Hello everyone, I am Hassan Sadali from ECA batch. I am here to explain the design and implementation of 3-bit synchronous up-down counter. And my group members are Ilango, Hemakmar and Kaviyarsan. Let's move on to the topic. Aim of this experiment is to design and implement the 3-bit synchronous up-down counter using the Multisim software. The required components for the experiment is one personal computer with a Multisim software. Let's see the concept of this experiment. When a counter is clocked such that each flip-flop in counter is triggered at some time, then the counter is said to be synchronous when clock is given at all flip-flop. Here it says the clock is given to all flip-flop, we say that is synchronous counter. There is no propagation problem. As the number of state increases, some involves complex propagation and it involves complex logic circuit. That means more number of JK flip-flop involves, the more complex of propagation and complex logic circuit occurs. Let's see what is counter. Counter is divided into two types. One is up counter and another one is down counter. Here we use 3-bit. Here we use 3-bit. 3 means that is 2 power 3. 2 power 3 is 8. Ranges from 0 to 7 value. Here in up counter, we give clock input. It gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Here we get output as 0, 0, 0 in first clock input, that is 0. Then it counts upwards from 1, 2, 3 up to 7. Here after 7 it counts continues to 0, not 8. Hence not 8 because there is no 8 in this range. So after 7 it comes to 0, then again 1, 2, 3, 4 up to 7. Here in this cycles repeat, that is up counter. Here in down counter, clock input gives 1, 2, 3, 4, 5, 6, 7, etc. Here it starts from 7 and it keeps downwards 6, 5, 4 up to 0 and again it goes to 7. Here also there is no -1 or 8. Then again 7, 6, 5, 4 in this cycle continues, that is down counter. Let's see the circuit diagram. Here we use 3 JK flip-flop for 3-bit. Clock pulse is given to 3 flip-flop because it is synchronous. Logic 1 is given to J and K point of first flip-flop. There is 4 AND gate and 2 OR gate and 1 NOT gate. We correct the circuit as follows. Here there is one up and down changer. We use 1 point for up counter and a 0 for down counter. Each Q point is a output point. First one is LSB nearer to clock pulse and the furthermost is a MSB. By this we can see MSB, LSB. We can see bit values. Example is 0, 0, 1. Example 0, 0, 1. That means this QA output working, it is not working, it is not working. Then it comes as 0, 0, 1. If only this is working, it comes as 0, 1, 0. Here is the example. Okay, let's see the Multisim software. Here is the circuit connected as per the circuit diagram. here is 1, that is up counter. Let's check the output. Here it comes from 1, 2, then 3, 4. This is up counter, so it counts upwards up to 7. Then again it's 7 after 0, 1, 2. The cycle difference. Okay, let's see from where we use these all equipments. JK flip flop. We can get JK flip flop from here. This is JK flip flop. Then AND gate, we use this, and again OR gate also we use. Here are the all equipments here. AND gate, OR gate, and JK flip flop from here. Then from source, we use this point, that is interactive digital constant. It is 0 and 1. We use switch for this, and we use NOT gate also here. It is digital thread. Okay, from here we use digital output DCD. From we use whatever color we want here. That is our for viewing graph we use four channel oscilloscope. This is called clock pulse also from source. Here are the equipments we get. Okay, now let's see the down counter. For down counter, it counts from 7, 6, 5, 4. Let's see it's correct or not. 7, then 6, then 5. Okay, let's see the graph for down counter. Okay, I change it for position to view it clearly. Let's see whether it's correct or not. For first clock pole, it is 1. It is 1. Then second, it is 2. This clock is 3. Then next to 4. And 5, 6, etc. For 1, all outputs are 0. So it is 0. For next clock, it is all is MSB. It starts from this 7. 1, 1, 1 is 7. 1, 1, 0 is 6. 1, 0, 1 is 5. 1, 0, 0 is 4. 0, 1, 1, 3. 0, 1, 0, 2. 0, 0, 1 is 1. Then again it comes from 0, 7, 6. This is the cycle works. This is down counter. Let's check its graph for up counter also. For 1 it is up counter. Let's see the graph. For first clock it is 0. Then second 1, 0, 1, 0 is 2. For third pulse 0, 1, 1 is 3. For fourth plus 0, 1, 0, 0 is 4. Then 5. Let's check it also. 1, 2, 3, 4, etc. For it is 0, sorry, it is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, 3, 4, etc. It also correct. 0, 1, 2, 3, 0, 1, 0, 4, 5, 6. It also 0, it cycles from upwards 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4. Like this it came. It's also correct. We get the output as correct. Another one is it is clock pulse is green, LSP is blue, then violet, then red. I forgot to say it. I changed the color for my observation. Okay, this is the up down counter. For graph, I also ready some picture. Let's see that once again. Here is the model graph for up down counter. Here 1 is up counter and 0 is down counter. For this, here to here is up counter. Then from here to here is down counter. Here again up counter, down counter. Because we change it to 1010 mode. For up counter, values ranges from 1, 2, 3, 4. When we suddenly change to down counter, it goes not 5, it goes downwards such as 3, 2, 1, 0. After we change it to up counter, it suddenly changes upwards. Example, after 7 not goes to 6, it goes to 0, 1. After we change to down counter, it's also downwards change. Example, not to 0, 7. This is how our down counter works. Okay. These are all the implementation of up down counter. Here the 3-bit up down counter was designed and implemented successfully. Here the experiment is over. Thank you.